So now we're going to go through section 11.4, which is all about tree diagrams. So far we've really only dealt with one possible thing happening: rolling a die, flipping a coin, picking a card. So there's very distinct outcomes, but now we're going to kind of combine events together. So these tree diagrams are going to give us a helpful way to determine all of our possible outcomes and what that sample space is, so that we can calculate probability of things occurring. So the first thing that's going to be super beneficial for us, if we are going to combine two experiments. So maybe I'm going to pick an item from this list, pick another item from this list of so many things. How many ways can I possibly do that? So the counting principle tells us the number of ways an event can occur. So if your first experiment can be performed in m distinct ways, and a second experiment can be performed in n distinct ways, then the two experiments can be performed in a total of m times n distinct ways. Okay? So what that means is if I have 5 ways to pick an object from this specific thing, 6 ways to do it for a second thing, in total I'm going to have a possibility of 30 outcomes. Listing all 30 is going to be quite tedious, so this tree diagram will actually help us with that. So let's start with an example we're used to. We're going to first flip a coin, and then we're going to toss a fair 6-sided die. We want to figure out what is every possible outcome. The first thing we're doing is tossing that coin. The second thing we're doing is rolling a die. So if you think of each of these events, the coin, there's 2 outcomes. You're going to get heads and tails. The die, there are 6 possible outcomes, 1 through 6. So in total, the counting principle tells us you have 2 outcomes for the first event. You have 6 outcomes for the second event. So in total, there are 12 outcomes. So I could flip heads first, and then I could get any one of those die options. Or I could roll a tails, get any one of those die options. So the best way I can show you what a tree diagram is by example. So we start off our tree right down here. Our first event, there's going to be 2 possibilities. So this event here will be flipping that coin. So our tree stems between those 2. Start here, stem it to here. So in our coin, there's 2 possibilities. You can get a heads or you can get a tails. Next thing that happens is we roll a die. So from the heads, we have 6 possible outcomes. So heads, we could roll this outcome. We could roll this one, this one, this one, this one, and finally this one. So we could roll heads, and then we could roll the die and get a 1, 2, 3, 4, 5, or 6. Same thing for tails. You could get a tails first, and then you have 6 possible outcomes. So you could roll 1, 2, 3, 4, 5, or 6. So from the tails, we stem off a few more. And those are all of our possibilities. So you can see it kind of forms a tree. You have a root back here, and then all of these branches that stem off of it. So the nice thing is, this now tells us exactly what our sample space is. Okay? You can start with the heads, and you can get a 1. So that's our first possibility. You get a heads and 2, heads and 3, heads and 4, heads and 5, heads and 6. the second branch gives you all these possibilities. So tails, and then one of the 6 dies. So if you add these up, there's 6 and 6, there's exactly all 12 of our outcomes. So now we don't have to worry about figuring out exactly what it is. So from this, now if I ask you what's the probability of getting a heads and an even number, you can now know your total event is 12, and you could, from the sample space here, figure out exactly how many are favorable to that specific event. Okay? So let's try it again. Now we're going to work with 3 possible events. So counting principle just extends. If you have more than 2, you just multiply the options together. So Dana's going to purchase 1 appetizer, 1 beverage, and 1 dessert from this list. So our appetizers, we've got 2 of them. We've got mozzarella sticks or guacamole. For the beverages, she's going to pick a soda or a lemonade for her party. And then for desserts, she's going to choose from pie, brownie, or cake. So we've got 3 possibilities. So we've got, in total, 2 here, 2 here, 3 here. If we want the number of possible outcomes in our sample space, you just multiply these together. So 2 times 2 times 3. She's got 12 combinations of food and beverages she can select for this party. So now that we know there's exactly 12, let's construct a tree diagram and then figure out exactly what that sample space would be. So we've got 3 events that can happen. Zoom out a little more, fit more page in. Okay. So we're going to start our root all the way back here. And our tree will stem off from that. So first, she's going to select an appetizer. Then she's going to pick a beverage. And then she's going to pick a dessert. Okay. So we've got 2 appetizers she can choose from. Those are the mozzarella sticks, so we'll label it with an M. And then guacamole. So we're going to start out by drawing 2 branches to those 2 different appetizers she could pick. Now when she goes to pick a beverage, she's either going to pick soda or she's going to pick lemonade. So she's got 2 options. She could pick soda and lemonade after she's selected the mozzarella sticks. Okay. And then from each of these, she's now picked mozzarella sticks and soda. She could pick 3 different desserts. So she could pick pie, she could pick brownie, or she could pick cake. If she selected lemonade, she could pick pie, brownie, or cake again. So from this option, we've got 3 branches. So from mozzarella sticks, she could go to soda and then go to any of these 3 desserts, or she can go through the lemonade branch and pick any of those desserts. Now the exact same thing can happen if instead she selects guacamole to begin with. She then could pick soda or lemonade. So we've got 2 options for our beverages. Then after she selects soda, she's going to have 3 options for the dessert. If she selects lemonade, same thing. She could pick pie, brownie, or cake. She could pick pie, brownie, or cake. So you can kind of notice these 2 are just clones of each other, okay? Because after that first decision, she still has the same options to go. But now this makes listing everything in our sample space a lot easier. So we're just going to label everything by numbers. Here's if she selects mozzarella sticks to begin with. Here's if she selects guacamole. Then she could pick soda, or she could pick lemonade. And then she's got the 3 options for the dessert for each of these to choose from. So we can list all 12 of our outcomes a lot easier now. Okay? But now this will help us with actually selecting our probabilities. So let's go back. Let's go ahead and even color code these a little bit more. Put brownies in brown. Let's do pie in blue. Make it a nice blueberry pie. And then cake, let's do gray. Okay. So what we want to see, now that we've got our entire sample space, is we want to determine the probability that she's going to select guacamole for the appetizer. So if you look, 6 of the outcomes are in green. So 6 of the 12 points in the sample space contain guacamole. So the probability of her getting guac is 6 over 12, which is 1/2. If she's going to select for the next one, lemonade and brownies, we've got this option here, that's lemonade and brownies. This option here is lemonade and brownies. So there's really 2 possible outcomes. She could select the mozzarella sticks lemonade and brownies or guac lemonade and brownies. So 2 of 12 lead to this event. So the probability of lemonade and brownies is 2 out of 12, or it reduces nicely to 1 over 6. Okay. So this way, when you have that tree already drawn, it makes it much simpler for you to go through calculating the probabilities, because every single event is listed here. You don't have to constantly think in your head, okay, well, what are my potential outcomes? You might miss some, especially when there's a lot more going on. So I would always recommend drawing a tree diagram when you've got a lot of stuff. Okay? So let's try another example. A hat contains 4 marbles. One's going to be orange, one's going to be pink, 1 blue, 1 green. We're going to pick 2 marbles from the hat, and we're not going to replace them. So basically, you're going to draw 1 marble first. That one, whatever you pick, stays out. You then have 3 left to pick from. So if we want to determine the number of possible points in the space, the first event has 4 possibilities. The second one, after you've picked that marble, you have 3 possibilities to choose from. So the number of outcomes is 4 times 3, or really, you have 12 possibilities. Okay. So we want to construct a tree diagram, and then we're going to go ahead and use that to calculate some probabilities. So we've got 2 events that are going to happen. You've got your first selection, and then you've got your second selection. Okay. So your first selection, you could select from 4 marbles. So we've got our tree, gonna have 4 roots. Your first option is you could pick an orange marble. Second option, you could pick a pink, you could pick a blue, or you could pick a green. Okay. Now when we look at the second marble, after you've made the selection of orange, you have 3 possibilities. Once you pick pink, same thing, there's 3 possibilities after this. And once you pick blue, 3 possibilities. Finally, green. Three possibilities. Okay. So once you've picked orange, you can't pick it again. So your only options are you could pick the blue or the pink marble, the blue marble, or the green marble. Those are the only remaining ones. When you pick pink, what's left is going to be the orange, the blue, and the green. If you pick blue first, you could pick the orange marble, the pink marble, or the green marble. Or if you pick green, you could pick the orange, the pink, or the blue. Okay? So these are all of your possible outcomes in this sample space. So if you want to list them all, your sample space would be right here. The thing you have to be careful about is you've got OP and then you've got PO. You also have, you could pick orange then blue or blue then orange. These are considered different events because they're happening in a different order. This one tells you you're picking orange first. This one tells you you're picking pink first. So they are different. The order is going to matter. Okay? But this is our sample space, all possible 16 outcomes in selecting a marble. And now we want to go through and we want to determine the probability we're going to select exactly one pink marble. Okay? So let's first look through and see which ones have pink. We select exactly one pink, exactly one pink, exactly one pink, 1, 1, 1. So in total, we have 6 events that select pink. So the probability of selecting a pink is 6 out of 12, or we have a 50% chance. So 1 over 2 is our probability. Okay? All right. Now, this one's a little bit tricky. At least one marble that is not pink. So it's really kind of natural to say, okay, those select something that's not pink. So does that. So does that. So does that. Well, you want at least one. In all of these other cases, this one, these, at least one's not pink. So at least one is still not pink. So really, every single event satisfies this. No event gives you pink. So the probability of at least one non-pink is 1. Okay? So remember, the probability of an event happening at least once, because it can get a little bit difficult, is 1 minus the probability the event doesn't happen. So this would be the probability of you selecting pink then pink. And that's never going to happen. Okay? So we're going to go through pretty much the same example, but now we're going to change it slightly. So we did without replacement. The only word that's changing is now we're going to do with replacement. So basically, I'm going to pick one marble out, notify or take note of what color it is, throw the marble back in the hat. Going to be able to pick it again. So if you want the number of sample points in this space, you have 4 times 4. So first, you pick from 4. You put that marble back in and return it, so you've got 4 to pick from again. So in total, you've got 16 possible outcomes. So now I have the possibility of selecting the same 2 marbles again. So I went ahead and I've already constructed this tree diagram. You first could select an orange, but then you could pick orange again. And then you have orange still as an option for everything. You could pick pink. In all of these cases, we've got green, just to keep things color-coded, and then finally blue. Okay? So in this specific case, you absolutely have the possibility of selecting the same color twice. So you can get orange and orange. You can get blue and blue. You can get green and green. So we can pick the same marble twice. Okay? So now, if we want to ask the same question we did in the last one, we want to determine the probability that at least one marble selected is not pink. So in this case, we do have an example. This one doesn't satisfy that criteria. So there isn't one marble that's not pink. But every other one is good. That's the only time that we select pink and pink. So we can use the same thing from last time. The probability of at least one non-pink is 1 minus the probability of them both being pink. So there's one chance out of the 16 that you're going to get pink and pink. So you have a 15 out of 16 chance of getting at least one non-pink.